Okay, welcome to the third installment of the Exploring the Frontiers of Incompleteness project. I just want to situate the present talk a bit. So the first talk of this series was by Hugh Wooden, and Wooden is a non-pluralist, or thinks there's a good case for non-pluralism regarding all of mathematics. So he thinks that there's a determinate truth value to statements like CH and the other undecided statements of set theory in mathematics. And you can classify the various pluralist views. Some people are non-pluralists about first-order arithmetic, and then pluralists about what lies above. And that was the position of our second speaker. So we've been working our way from ultimate non-pluralism about the universe of sets down to non-pluralism about first-order arithmetic. And today's speaker is a much more radical pluralist. He's a pluralist about pretty much everything. So it's great to have Joel Hamkins as our third speaker.
Well, thanks very much. It's really a pleasure to be part of the EFI series here at Harvard. The other talks look really interesting. So I'm really happy to be here and to tell you about the multiverse perspective on determinateness in set theory. So let me just begin by mentioning that set theorists commonly take their subject to serve as an ontological foundation for the rest of mathematics, in the sense that other abstract mathematical objects can be construed fundamentally as sets. And in this way, they regard the set-theoretic universe as the realm of all of mathematics. So on this view, mathematical objects such as functions, groups, real numbers, ordinals, and so on are sets. And being precise in mathematics amounts to specifying an object in set theory. So I'm describing this view, but there's a weakened version of it which remains compatible with structuralism, the view that not that mathematical objects are specific sets, but rather they're determined by the role that they play in connection in structural relations with other mathematical objects. And so you can weaken this kind of view to the position that set theory provides sets that provide those objects fulfilling those desired structural roles. For example, of the real numbers as the complete ordered field and so on. So let's just lump these two kind of views together as the view that set theory provides the foundation or a foundation for the rest of mathematics, in the sense that mathematical objects can be viewed as sets. So these sets accumulate transfinitely to form the universe of all sets, and the picture that set theorists often draw in this situation is the cumulative universe, so a giant V. So as you go to higher and higher levels, you get more and more sets. So maybe we call this V sub alpha. And so the cumulative universe is therefore regarded by set theorists as the domain of all of mathematics. Since this cumulative universe contains all sets, all mathematical objects exist in that universe. So this orthodox view I'm talking about then among set theorists exhibits a twofold realist or Platonic nature. First of all, mathematical objects exist or can exist as sets, and secondly, these sets enjoy a real mathematical existence accumulating to form this universe of all sets. So the principal task of set theory on this view is to discover what are the fundamental truths of this cumulative set-theoretic universe, and those truths will include all mathematical truths. So I would like to emphasize that on this orthodox view, the set-theoretic universe is held to be unique. It's the universe of all sets. So interesting set-theoretic questions such as the continuum hypothesis and other questions will have a definitive final answer in this universe. And the fundamental problem for set theorists on this view is how to find out what are these final truths. So let me describe as the universe view the position that there is this unique absolute background concept of set, which is instantiated in the cumulative universe of all sets, in which all set-theoretic assertions have a definite truth value. Therefore, this universe view is highly deterministic for set-theoretic truth, and therefore also for mathematical truth. Okay. So adherents of the universe view often point to the increasingly stable body of regularity features flowing from the large cardinal hierarchy, such as determinacy consequences and the accompanying uniformization and Lebesgue measurability properties in the projective hierarchy of sets of reals. So I'm thinking here about, for example, the fact that if you have sufficiently many large cardinals, then you get projective determinacy, and therefore all projective sets are Lebesgue measurable and have the property of pair and have the perfect set property and so on. So those are very nice features. And these regularity features are both mathematically desirable and highly explanatory. They provide a unifying account of the mathematical truth that we would like to see even at lower levels of the universe. So therefore, the large cardinal perspective seems to provide a coherent unifying theory of those. And the situation is taken as evidence that those hypotheses are putting us on the right track towards the final answers to those set-theoretic questions. So the fact that we get these regularity consequences of the large cardinal axioms is taken as evidence for this universe view. But meanwhile, there's another phenomenon, the pervasive independence phenomenon in set theory, so by which we have come to know that numerous set-theoretic questions cannot be settled on the basis of ZFC. I mean, questions such as the continuum hypothesis and many, many other instances. These are viewed as a distraction. So on this view, independence is an irrelevant side discussion about provability rather than about truth. Independence is about the weakness of our theory in finding the truth rather than about the truth itself. So the independence of a set-theoretic assertion from ZFC tells us little about whether it holds or not in the universe. It just tells us about the power of that axiomatization to find the truth. Of course, if you have a weak theory, then you should expect pervasive independence. Because, of course, a weak theory is weak. What it means to be a weak theory is that it doesn't settle questions. So when you have a weak theory, then you expect to have a lot of independence. And so this kind of situation with this pervasive set-theoretic independence, I mean, independence from ZFC and even ZFC from ZFC plus stronger axioms, is evidence only that those theories are weak and that we're in need of strengthening it. On the universe view, that is. Okay, so let me make an opening thrust against this universe view, and something that I find to be a difficulty or even a paradox for the universe view, and that is, while adherents hold that there's a single universe of all sets, nevertheless, the most powerful tools that have been developed in the past half-century are most naturally and directly understood as methods of constructing alternative set-theoretic universes. Universes that seem fundamentally set-theoretic. So I'm speaking here about forcing and ultrapowers and canonical intermodals and so on. We have many, many tools, but principally I'm thinking about the case of forcing. So much of set theory over the past half-century has been about constructing as many different models of set theory as possible, and these models are often made to exhibit precise, exacting features or specific relationships with other models of set theory. Let us imagine that set theory had followed a different history than it did follow. So let's suppose, for example, that 100 years ago, as set theory was developing, theorems were increasingly settled in the base theory, or that maybe the few independence results that arose were limited to paradoxical seeming metalogic statements, self-referential statements, and things of that nature. Let's suppose that the independence results that did occur, the real ones, were settled by some missing self-evident set principles, say in the way that occurred with the addition of the replacement axiom to ZFC or with the addition of the axiom of choice to ZFC. So those axioms were added because it was felt that they were expressing part of the intended meaning of set, and they settled questions at that time that were being considered. So let us further suppose that the basic structure of the set-theoretic universe became increasingly stable and agreed upon as history proceeded. Okay, if that had happened, then we would have strong evidence for the universe view that we were on the right track. But of course, the actual history is nothing like this at all. It's completely the opposite. So over the past half-century, set theorists have discovered a vast diversity of models of set theory. It can only be described as a chaotic jumble of set-theoretic possibilities. So whole parts of set theory exhaustively explore the combinations of statements realized in various models of set theory and study the methods supporting this exploration. So I'm thinking here about, for example, the field of cardinal characteristics of the continuum, where you study the bounding number and the dominating number and so on, and there's a whole family of different cardinal characteristics which are separated in various combinations and complex diagrams showing the different combinations that are possible. And much of the theory is explicitly about finding models to witness various separation possibilities. and also about studying the tools that are used in order to do that. For example, iterated forcing and proper forcing and so on. Much of the analysis of those different forcing methods arose out of consideration of separating various cardinal characteristics, hierarchy. So, for example, would you like to have the continuum hypothesis but not diamond? Would you like to have 2 to the aleph n equal to aleph n plus 2 for every n? Would you like Sussman trees? Would you like to separate the bounding number from the dominating number? Do you want an indestructible, strongly compact cardinal? Would you prefer that it's also the least measurable cardinal? All of these things are possible, and set theorists can make models to order. Okay, so as a result, set theory, the fundamental object of study in set theory has become not set or any set construction, but rather the model of set theory. So group theorists study groups, ring theorists study rings, set theorists study models of set theory. So we have, for example, the constructible universe. We can adjoin various objects like 0 sharp. We can look at the canonical inner model of one measurable cardinal. We can look at a sequence of extenders if we want more large cardinals. So we have various models with large cardinals, forcing extensions of them, ultrapowers, these various cutoff universes in various sense, in the L hierarchy, the D hierarchy, the H hierarchy. We have other universes, L of R, the hereditarily ordinal definable sets, generic ultrapowers, Boolean ultrapowers, and on and on and on. So forcing especially has led to a staggering variety of different models of set theory. So we have what can only be described as an entire cosmos of set-theoretic universes connected by forcing or large cardinal embeddings. And as a result, set theory now exhibits a category-theoretic nature where we have a bunch of possible worlds connected by these various set-theoretical relations. So the challenge that I make to the universe view is to explain this central phenomenon, the phenomenon of the enormous diversity of set-theoretic possibilities. So the universe view seems to be fundamentally at odds with the existence of alternative set-theoretic universes. Will they be explained away as imaginary? It seems that they must, if you hold the universe view. In particular, I want to emphasize that it does not seem sufficient when arguing for the universe view merely to identify a particularly robust or clarifying theory if the competing alternatives still appear acceptably set-theoretic. It doesn't matter if you describe the most beautiful neighborhood in the city, it doesn't mean that the bad neighborhoods somehow don't exist. You still have to explain away the pluralistic illusion that we have from these alternative set-theoretic models. So, okay. So the competing philosophical position that I want to discuss accepts the alternative set concepts as fully real. The multiverse view is the position holding that there are many set-theoretic universes. The view is that there are numerous distinct concepts of set, not just one absolute concept of set, and each corresponds to the universe of sets to which it gives rise. So I'll make a kind of identity between the set concept and the universe of sets to which it gives rise. Okay. So the various concepts of set are simply those that give rise to the universes that we have been constructing for the past half century. So one of the key observations is that from any given concept of set, we're able to generate many new concepts of set relative to it. That is, the alternative universe construction methods that we have are relative constructions. You start with a model of set theory and build another model of set theory from that one. So from a set concept giving rise to universe W, we can describe the universe, the constructible universe from the sense of W, or the hereditarily ordinal definable universe in the sense of W, or the L of R of W, or the core model of W, or forcing extensions of W of various kinds, or ultrapowers, and so on. So each such universe amounts to a new concept of set, which is described in relation to the concept W. So many of these concepts of set are closely enough related that they can be analyzed together from the perspective of a single set concept. And this is the interesting thing. What might have been a purely philosophical enterprise of comparing different concepts of set becomes in part a mathematical one precisely because set theory is able to mathematize these relations in many cases. Not all cases. Not every model of set theory is able to refer to all of the other models of set theory that are possible. But in many cases, it is. And so, to my way of thinking, this explains why this emerging area of philosophy of set theory, which is becoming so interesting, is a fascinating mix of extremely technical mathematical ideas with profoundly philosophical matters. We want to compare these alternative set concepts, and furthermore, many of the questions that we want to ask about that situation can be mathematized and admit of mathematical answers. So it also explains, to my way of thinking, why the field is extremely difficult, because what it requires is researchers who are familiar both with the technical issues that arise in set theory and also have the philosophical ability and philosophical frame of mind to analyze them philosophically. Okay. I want to present the multiverse view as a brand of realism. That is, these alternative set-theoretic universes arise from these different concepts of set, each giving rise to a universe of sets which is fully as real as the universe of sets on the universe view. So on the multiverse view, each individual concept of set is fully as real as the universe that the universists are talking about. It's just a different concept of set, not a lesser one. So the view in part is that our mathematical tools, forcing and so on, have offered us glimpses and provided evidence for the existence of these other mathematical worlds. A Platonist may object at first if you think that Platonism is connected with the idea that there's a unique set-theoretic universe rather than a real one. But actually, the multiverse view is a kind of Platonism, namely it's Platonism about universes rather than merely sets. So it's a kind of second-order realism. And part of my thesis is that set theory is mature enough to adopt and analyze this view. So the multiverse view places a focus on the connections between the various universes, such as the relations of ground model to forcing extension or model to ultipower. And this is one important way it's distinguished from formalism. That is, that on the multiverse view, the important thing is the connection between the models rather than just looking at each individual model separately, or each individual, say, formal system separately. And to give a kind of instance of that, many of the early forcing results were stated merely as relative consistency results. So starting with a model of phi and producing psi in a forcing extension, the theorem would be stated as if ZFC plus phi is consistent, then ZFC plus psi is consistent. But in contemporary work, it's almost never stated that way if it was a forcing argument. Rather, the theorem would be if phi holds, then there's a forcing extension with psi. And furthermore, it would be stated what kind of forcing it was. Is it CCC forcing or proper forcing, and so on, because all of that information about the relationship between those two models with phi and psi is important for the further study of the context of this implication. So it retains that important information connecting the models. Okay, the central dispute, of course, between the universe view and the multiverse view is whether there are universes outside of V taken to be the universe of all sets on the universe view. There's less of an issue about the inner models because, of course, even the universes can say, well, yes, there are these inner models that satisfy some certain properties, and that seems less problematic. If you're committed to this enormous universe, then you can define inner models that are classes and so on. So the issue tends to be, the sort of point of contention between the views is about the existence of outer models of the universe, and a special case of that, to my way of thinking, captures really the full debate, which is, do forcing extensions of the universe exist? So on the universe view, forcing extensions of the universe are an illusion, and that this is what needs to be explained away. But on the multiverse view, V is merely an introduced constant referring to whatever universe is currently under consideration. So forcing extensions of V exist, and when you go to those universes, then you have a new V, in a sense. Okay, before I proceed, let me just say a little bit more about some technical matters about how forcing works. So we start with a model of set theory, which I'll call V, and we have a partial order in V. And then supposing that we have a V generic filter in P, and that means that G contains members from every dense subset of that partial order in V, then we build this new model, V of G. One way to think about it is something like a field extension where you adjoin a new root of a polynomial, say if you look at field extensions of the rationals. Here we're adjoining this new ideal object G, and we simply close V, add G, and then close under the elementary set building operation, so that every object in the forcing extension is definable algebraically from objects in the ground model and this new object G. It's quite remarkable that the forcing extension V of G constructed in this way is always a model of ZFC set theory. But the point, part of the power of the technique, is that it can be made to exhibit different set theoretic truths in a way that can be precisely controlled by the choice of the partial order P. So by choosing different P's, we can control the truths of this model, and this is where the power of forcing comes from. So another way to look at how forcing works is that forcing extensions are really the classical projections of multi-valued logic approach to set theory. So if you, for example, have a complete Boolean algebra B, and you have the idea that you want to undertake set theory in a multi-valued logic setting using truth values from B, from this Boolean algebra B, then you'll be led very naturally to the concept of B names, which are the sort of hereditary set concepts that use B-valued truth. So merely the idea of doing set theory in a multi-valued logic setting with a Boolean algebra leads directly to the concept of B names and to the Boolean valued universe VB. And the projections of this universe by taking a quotient by an ultrafilter are in essence exactly the forcing extensions. So the remarkable fact here is that merely saying you want to do set theory in a multi-valued logic setting, the remarkable fact is that the truths, the resulting truths of the models that you get depend highly on which truth values are available. In other words, it depends on B. So by choosing this Boolean algebra B differently, you're led to a very different theory in V of B. So choosing the Boolean algebra is essentially the same as choosing the partial order on the previous slide. Okay. So the point is that this way of looking at the situation of the forcing extension really shows that it really is a different set concept. It's just the projection of a multi-valued logic approach to set theory modding out by an ultrafilter. This is a legitimate concept of set. It leads to universes that satisfy ZFC, but also satisfy other truths, different truths, depending on the Boolean algebra that's used. Okay. Traditionally, forcing was often used with countable transitive ground models. This is how Cohen first did it and how it was done. It's often done that way. So one starts with a countable transitive model of set theory. And since M is countable, it has only countably many dense sets, and so one can easily construct an M generic filter for the partial order by diagonalizing. You enumerate the dense sets, and then gradually pick a descending sequence that gets inside all of those dense sets. So you can very concretely find the M generic filter. And in fact, in terms of the Turing degrees, if you have an oracle for M, if M is a countable transitive model, so therefore it's essentially coded by a real number, and if you imagine having a real number on a tape of a Turing machine for that model, then in a computable way, you can produce a code for the forcing extension. So therefore, every countable model is Turing equivalent to some of its forcing extensions constructed in this concrete way. Okay. So there are a few drawbacks of this countable transitive model approach to forcing. I refer to this in other contexts as the toy model approach to formalization. The idea is that it was easy to construct the generic filter because M was this countable model. It's a kind of toy model, a substitute universe, not the real universe, but just a kind of fake substitute universe. Some of the drawbacks of the method are that there are many mathematical issues with the existence of countable transitive models of ZFC. You can't prove they exist. It's a strictly stronger assumption to assume that there's a countable transitive model. that issue is addressed by just dropping transitivity. In fact, you don't need transitivity for that argument, although it's quite often assumed that the model is transitive. In fact, if you just omit that, everything works fine and it completely addresses that objection. But it's very rarely done that way because there's a kind of default preference in set theory to work with well-founded models. Also, this approach to forcing is limited to forcing only over some models, the countable transitive ones. And so we don't have, on this account of forcing, a general theory, for example, of can we express the idea that a statement is forcible, is true in a forcing extension, or true in all forcing extensions, and so on. The other approaches to forcing enable you to make sense of these kind of questions, but here you're only forcing over some models. Also, the countable transitive model approach pushes much of the analysis of the independence proofs inappropriately into the meta-theory. Okay. So a more sophisticated approach to forcing develops the technique within ZFC as an internal set-theoretic construction so that one can force over any model of set theory, whether it's a countable transitive model or not. So we want to make the move from forcing over a tiny model M, a toy model, to forcing over the entire universe V. And my former student, now colleague Jonas Rietz, refers to this as removing the training wheels, because if you think about the letter M syntactically or typographically, then you can turn it into the letter V by removing these two bars on the outside, and you take the training wheels off, and then you're forcing over V. And so it's a happy day when, with my own students, we finally take the training wheels off and do forcing over V. Okay, so there's a variety of ways to accomplish this. Right. Okay, so those who take the universe V as the unique universe of all sets will object that there are no, let me just back up a bit here. So, okay. So, sometimes you hear the objection, there are no V generic filters. I've seen this in print in a number of cases. And surely we all agree that for non-trivial forcing notions, there are no V generic filters in V. So it seems to be problematic if you're developing a theory of forcing over V, and V is absolutely everything, then of course there won't be any V generic ultrafilters available for you. But to my way of thinking, this is like saying there is no square root of -1. Of course, the square root of -1 does not exist in the reals. You have to go to the field extension to the complex numbers to find the square root of -1. Similarly, you have to go to the forcing extension to find G. Historically, of course, the square root of -1 was very suspicious. It was imaginary, but very useful. Eventually, mathematicians realized how to simulate the complex numbers inside the real numbers. You can think of this complex number as represented by a pair. Maybe this pair, you think of it as a name for that complex number. And thereby, even if you only believe in real numbers, you have a measure of access to the complex numbers in that way. But the case of forcing is very similar. We don't have the generic filter inside the universe V, but we do have a measure of access to the forcing extension because of we have all of the names that are used to build it, and we have the definability of the forcing relation and Boolean values and so on. Okay. So let me describe what I call the naturalist account of forcing, which is a way of axiomatizing and proving legitimate the practice of forcing over V. So suppose that V is a universe of set theory and P is a notion of forcing, then I claim that there's a class model of the theory describing what you want to be true in the situation of a forcing extension. So if you write down the theory of what it's like to live in the forcing extension, what would you want to be the case? Well, the language will have the set membership relation and will also have constant symbols for every element of V. And also we want to have the ground model as a class in the new model. So we have a class predicate for that ground model. And I want a new object G. So I'll have a constant symbol that's representing the generic filter. And if you write down the theory of what you want to be true here, well, what you want to be true is that, first of all, everything that was true in V is still true in the interpretation of V. So So the elementary diagram of the old universe relativized to that predicate that you added. So everything that you knew before about V, you still know it about V. Also, we add the assertion that that predicate is a transitive proper class, and that G is a V generic ultrafilter on P, that ZFC holds in the new universe, and furthermore that the new universe is V of G, meaning that everything in V of G is the interpretation of a name, a P name in V by that filter G. So that theory, so the theorem is that it's a theorem of ZFC that for any partial order P, there's a definable class, definable from parameters, a definable class model of this theory. Now, it's really a theorem scheme because of issues relating to the Tarski's definability of truth. There's a definable class that satisfies, as a theorem, every instance of this theorem. It's because you can't really say the full elementary diagram of V is true in V. This is a truth predicate and so on. So it's just every instance of it is asserted of the class. So there's a definable class that satisfies this entire theory. This naturalistic account of forcing exactly legitimizes the use of forcing that you see in practice, in the set-theoretic literature. In any set-theoretic context, a set theorist might, if it's ever convenient, a set theorist says, look, I've got this partial order, let G be V generic, and now argue in V of G. And then they continue arguing. And everything that they knew before about V, they still are using that in their argument. So this kind of magic phrase here is exactly invoking this new theory. So whenever you see this in a set-theoretic article, what it really means is an invocation of this theorem. I mean, of course, there's other ways that people can use to explain this phrase. Maybe they say, well, what I really mean is this accountable transitive model and so on. But the naturalistic account of forcing makes it just completely legitimate as it is. You can argue in V of G means you're now working in this new theory. OK, there's a kind of semantic version. The previous one was a syntactic version with a theory. Now there's a semantic version with a model. For any notion, for any forcing notion P, the universe has an elementary embedding into a class model V bar, which has a forcing extension inside V. So in other words, there's a class model V bar inside V, and there is an object G, which is V bar generic for the image of the forcing. And the whole thing lives inside V. So V has the elementary embedding, and it has these classes, and it has the object G. So this is a way of understanding it. This is the model. This V bar of G is the model of the previous theorem that satisfies that theory. The fact that we're satisfying the elementary diagram of the ground model is exactly asserting that that map was an elementary embedding. But there's no guarantee that that map is onto, and in fact, it can't be if the forcing is non-trivial. So this map, this elementary map, is also, it's the same thing as what I've called the Boolean ultrapower map. OK, so I'd like to set up an analogy between the set theory and geometry, the situation in geometry. And the analogy is that the one true universe of sets on the universe view is to the set-theoretic multiverse on the multiverse view as the one true geometry is to the spectrum of Euclidean and non-Euclidean geometries. So for hundreds of years, or perhaps thousands of years, geometers studied the geometrical concepts of points, lines, and planes with a seemingly clear absolute meaning. And I would like to separate the issue about geometry as a study of actual physical space as opposed to the sort of mathematically idealized geometry. I'm just talking about the mathematically idealized geometry. There was, prior to the rise of non-Euclidean geometry, the idea that point, line, and plane, sphere, and so on referred to unique objects at unique absolute geometrical concepts. But those concepts shattered in the rise of non-Euclidean geometry into a spectrum of different distinct geometrical concepts realized in the various non-Euclidean geometries. So the first consistency arguments for non-Euclidean geometry presented them as simulations within Euclidean geometry. For example, in spherical geometry, So if you think about a sphere, then the concept of line could be temporarily interpreted as a great circle on the sphere. And, and if you think of the parallel postulate for this account of line, then you see that it's going to fail in spherical geometry. In hyperbolic geometry, you think of the concept of line. You fix the unit circle, and you think of the concept of line as circles that are perpendicular to the edge, and that's your concept of line in hyperbolic geometry. So you have sort of embedded copies, reinterpretations of the geometrical concepts using Euclidean concepts, but they happen to satisfy different geometrical truths, namely the failure of the parallel postulate. So in time, geometers accepted, however, the alternative geometries more fully with their own independent existence. In other words, the idea is, do we understand spherical geometry only because of its copy in 3-space, in Euclidean 3-space, or do we understand it as its own geometry that we could live inside, and what would it be like to live inside such a geometry? So that view maybe is connected with the view of sort of physical realization of geometry, because if the actual physical universe has a geometry that's not Euclidean, then you can't very well argue that it's incoherent to think about actually living in those worlds, because we probably do live in such a world. So today, geometers, of course, have a deep understanding of these alternative geometries, and no one regards the alternative geometries as illusory. So I'm reminded of some videos I've seen on YouTube connected with Bill Thurston, I believe, about what it's like to wander around in various hyperbolic spaces and so on. And it's really quite incredible. You can see all kinds of more, very high dimensional thing with lots of right angles and so on. And as you move around, it all seems perfectly coherent and beautiful. Okay, so this analogy extends to the way that the mathematicians reason about these different worlds, namely, geometers reason about the various geometries sort of externally as embedded spaces like they were originally discovered, but also internally by, in effect, living inside these alternative geometries and exploring them, developing their intuitions. But also they analyze them abstractly by, say, specifying an isometry group that's preserving the geometry. So this is, in fact, one of the most common ways to specify such a geometry. In the case of forcing, it's exactly the same. Namely, we understand the forcing extension from the perspective of the ground model. This is like an embedded copy of it by looking at the names and the forcing relation. We also understand the forcing extension by jumping inside, by arguing in V of G, and this is what the naturalist account of forcing is telling us. But we also understand the forcing extension by analyzing, say, the automorphism group of the forcing relation itself in terms of homogeneity properties and so on. So there's in mathematical history, of course, puzzling mathematical objects have come to be accepted as fully real. Irrational numbers such as the square root of 2 were eventually accepted. 0 became a number, negative numbers, complex numbers, non-Euclidean geometries. And now is the time for V-generic ultrafilters. Okay. Now the universe view is simulated inside the multiverse view by fixing a particular universe. Now in the multiverse view, we have this spectrum of possible universes, and the multiverses can understand the universe perspective by saying, yes, you're really just picking one and saying that's the real one, and just working below that one universe and not ever talking about the universes outside that universe. So when you do that, in effect, you've provided absolute background concepts of countability, well-foundedness, and so on, namely the concepts provided by that one universe. So from the multiverse perspective, the universe view appears to be exactly like this, picking one and saying that's the real one, and I'm only going to look below that universe. So this means that the multiverse is able to understand what the universe is talking about by means of this kind of translation. But also the multiverse view, the multiverse is able to adjudicate differences of opinion between various universes, because maybe somebody wants to fix this universe and another universe person says, no, no, it's like this. And this is a debate, of course, that occurs in the context of a multiverse view. So we can have that discussion in the context of a multiverse view. So let me turn now to what I'm calling case study of two hypotheses, namely the continuum hypothesis and V equal L, and explain the multiverse perspective on these two axioms. So the continuum hypothesis is the assertion that every set of reals is either countable or equinumerous with the reals. So this was, of course, a major open question from the time of Cantor. It was the first problem on Hilbert's famous list of open problems at the dawn of the 20th century. It's now known by results of Gödel and Cohen to be neither provable nor refutable from the usual ZFC axioms of set theory. So Gödel proved that CH holds in the constructible universe L, and Cohen proved that L has a forcing extension where the continuum hypothesis is false. So, but more important than mere independence is the following fact. Namely, every model of set theory has two mild forcing extensions, one of which collapses null cardinals and satisfies the negation of the continuum hypothesis, and the other of which adds no real numbers and satisfies CH. So every universe has a forcing extension where CH is true, and another one where CH is false. So therefore, they're both easily forcible, and we can, in effect, turn it on and off like a light switch by going to further and further forcing extensions. We can make it true, and then false, and then true, and then false, and so on, by just moving to a larger set-theoretic universe. And it's more than just that. We have a deep understanding of how the continuum hypothesis can hold and fail densely in the universe. And we have a very rich experience in the resulting models. Perhaps some of the people in this room have flicked that light switch many, many times. So we know in a highly detailed manner whether one can obtain the continuum hypothesis or its negation over any model of set theory while preserving any number of other features in the model. Oops. So the multiverse position on the continuum hypothesis is that this is a settled question. It's incorrect to describe CH as an open question. And the answer consists of that detailed information that I just described on the previous slide. Namely, it's our detailed understanding of how the continuum hypothesis both holds and fails throughout the multiverse. So how those models are connected and how we can reach one of them from another and so on, while preserving or omitting certain features. So of course, there remain fascinating open questions about the continuum hypothesis and about whether you can attain it with this property or with that property and so on. But the most important essential facts of the situation are known. So in particular, let me go beyond this. I'm going to argue that the continuum hypothesis can no longer be settled in the manner that set theorists formerly hoped that it might be. So this is the dream solution template for the continuum hypothesis. So the way that everyone wanted to solve the continuum hypothesis was by undertaking the following two steps. First, you were supposed to introduce a set-theoretic principle phi, which expressed an obviously true set-theoretic statement. So, I mean, obviously true in the same sense that many people find, say, the replacement axiom or the axiom of choice to be obviously true and part of what we mean by the concept of set. So you produce a statement that everyone agrees is part of what we meant by set, and then the second step is to prove that that statement determines the continuum hypothesis, either by proving that it implies it or that it implies the negation. So if you could carry out these steps, then of course you would solve the continuum hypothesis problem because everyone would accept this obviously true principle as part of what we meant all along. And therefore, they would also accept its consequences because of the proof. And so we would have a solution of the continuum hypothesis. OK. So I argue that this template is not workable. It will never happen. And the reason is that because of our rich experience and familiarity with models having CH and with other models having not CH, the mere fact that you've succeeded in step 2 immediately casts doubt on its naturality for step 1. So if you prove that, say, phi implies CH, then immediately we cannot accept it as obviously true because we already know set-theoretic worlds where not CH was the case. And they seem perfectly set-theoretic to us. So success in the second step exactly undermines the first step. because of our rich experience in worlds having CH and not CH, if you have a principle implying CH, then I can say, yeah, but what about these other worlds where CH was false? It's perfectly set theoretic, therefore your principle is not obviously true. And similarly, the other way. So the point is that the objection will come from a position of deep experience with set theoretic situations of the contrary situation. So let me give an example to illustrate this reaction to a kind of dream solution template. So Freiling proposed his delightful axiom of symmetry, what he called a simple philosophical proof of not CH. This is in his paper in 1986. So the axiom of symmetry is the assertion that for any function f, mapping reals to countable set of reals, to countable sets of reals, there are two reals x and y, so that y is not an element of f of x, and x is not an element of f of y. So the idea is that, let me go over here. Okay, so here's the real line. And we're associating each point with a tiny set, some countable set. So if this is x, then f of x is some countable set of forbidden points. And the idea is that we should be able to find, the axiom says we should be able to find a pair of points so that y is not in f of x and x is not in f of y. And Freiling justifies this axiom as obviously true. He makes an extended philosophical argument for this axiom, which is prior to any concept of measure and appeals to the pre-reflective principles that people had used to justify, for example, the fact that measure should be countably additive. He appeals to those basic intuitions about the concept of measure, the most basic ones, and says that they justify this axiom. So the way he argues is, to give a very simplified account of his argument, he says, well, what you should do is imagine throwing two darts at the real line, x and y. They land at x and y. And now consider the first one, x. Since f of x is this countable set, this tiny set, almost surely y is not an element of f of x. But then, by the symmetry of the situation, it shouldn't matter that I chose x as the first one. I could do the same thing by considering the second one. And so the symmetry of the situation leads me to expect also that almost surely x is not an element of f of y. And therefore, the principle is obviously true. So what he says is, okay, the principle only says that there is at least one pair. But the intuitive argument shows that almost every pair, almost surely, if you throw two dots, you'll have an instance of the phenomenon. So the axiom only says at least once, but the intuition says every time, right? So what he writes is actually the axiom being weaker than our intuition does not say that two dots have to do anything. All it claims is that what heuristically will happen every time can happen, that is, can happen at least once. Okay, so Freiling has carried out step one of the template. He has a set theoretic principle and argues that it is obviously true. And then he does step two. Namely, it's exactly equivalent to the negation of the continuum hypothesis. So let me just give a quick proof of that. If the continuum hypothesis is true, then we can well order the reals in order type omega 1. And so every initial segment of that well ordering is a countable set. So I associate each point x to its predecessors in the well order. That's a countable set. Now if I have any two real numbers x and y, one of them must come earlier than the later one, and therefore it will be in f of the later one. So therefore, it's not possible in that situation to have two such that neither is in f of the other. And conversely, if the continuum hypothesis fails, then if you have Aleph 1 many reals x alpha, if you take f of x alpha is a countable set, so we've got here Aleph 1 many countable sets, and under not ch, that's not all the reals. Therefore, there must be some real that's not in that union. But f of y is a countable set, and so it contains only countably many x alpha, so there must be some x alpha that's not in f of y. And so again, we have 2 points. I mean, not again, but rather, so we have 2 points such that neither is in f of the other. So if CH is true, then the principle is false, and if CH is false, then the principle is true. So it's exactly equivalent to not CH. So he's carried out the dream solution template to CH. And so the question is, it was proved in 1986. Was it received as a solution of CH? And the answer is no. So many mathematicians completely ignored his philosophical pre-reflective appeal for the axiom, and instead they objected from a perspective of deep experience with non-measurable sets. So the typical reaction to Freiling's proposal is that the set of pairs xy, so that x is an element of f of y, might not be measurable, and the intuition is based on the idea that that set is a measurable set. So this objection is coming from experience of subsets of the plane. So if you think of the real plane, you can have subsets of the plane such that all of the vertical sections are countable, and all of the horizontal sections are the complement of a countable set. And so if you look at it this way, the set looks very small, but if you look at it this way, the set looks very big. And so, so this is the kind of weird sets that come up, and the measure theorists were used to that, these kind of violent counterexamples to naive ideas about measure. And so the objections were made to the axiom of symmetry on the basis of these kind of ideas. So we've become skeptical of those naive uses of measure precisely because we know about these very badly behaved examples. And it's because of that detailed experience that we're not convinced that the axiom of symmetry is intuitively true. So the situation is exactly how I predicted any solution of CH has to be. It's exactly followed. OK, and similarly for any other dream solution of CH. So let me give another example showing that pattern. Namely, consider the following set-theoretic principle, what I call the power set size axiom. So the axiom says that whenever one set is bigger than another, then it has strictly more subsets. So we can write it like this. If x is strictly less than y in cardinality, then the power set of x is strictly less than the power set of y in cardinality. So set theorists understand this axiom very, very well. But before I tell you about the set theorist's reaction to it, let me just tell you about the non-logic mathematician's reaction to the axiom. If you go to the math department and you say this principle to a non-logic mathematician, then they will like it very much. And they're also likely to expect that it's a theorem. So many mathematicians, this principle is simply obvious. And it's as appealing, for example, as the axiom of choice. People really like this axiom. And if you don't believe me, then just please ask your colleague, try it out, and you'll find some that really like it. But meanwhile, set theorists almost universally reject this axiom when it's proposed as a fundamental axiom. And why is that? Well, it's because we know how to achieve all kinds of crazy patterns for the continuum function. For example, by Easton's theorem, it's very easy to violate the power set size axiom. Cohen's model, in fact, has 2 to the omega equal to 2 to the omega 1. When you add all of too many Cohen reals, you end up with a violation of this principle where the countable set and the set of size Aleph 1 have different cardinalities, but their power sets have the same size. So Martin's axiom violates it if CH fails. Lucent's hypothesis violates it. The power set size axiom fails under many of the forcing axioms, such as PFA or Martin's maximum, that are often particularly favored by set theorists with the universe view. OK, so the situation is that we have a set theoretic principle which is many mathematicians find to be obviously true, which expresses an intuitively clear pre-reflective principle about the concept of size, and furthermore, which set theorists know is safe. We have a consistency proof. It's a consequence of GCH. It's a weakening of GCH. So we know it's relatively consistent. But nevertheless, it's almost universally rejected by set theorists when it's proposed as a fundamental axiom. And the reason is that we're simply too familiar with the ways that the power set size axiom can fail, and we have too much deep experience working with models of the contrary situation. But it's easy to imagine an alternative history to set theory. Say, in the early days of set theory, maybe the question arose whether, say, the symmetric group on sets of different cardinality could be isomorphic. It's a very natural question. If you have a smaller set and a bigger set, and you look at the permutation groups and you want to know, can those groups be isomorphic? Well, if you have the power set size axiom, then it's easy to see that they can't be isomorphic because, in fact, they have different cardinalities on the basis of that axiom. With an ordinary ZFC, they might have the same cardinality, and that argument doesn't work. In fact, nevertheless, it's true. In ZFC, you can prove that the symmetric groups on sets of different cardinalities aren't isomorphic, even when they have the same cardinality. But it's a deep argument. But one could use the PSA axiom to settle that argument. So imagine a different history, and imagine that question arose, and it was answered that way on the basis of the PSA axiom. Then I can also imagine that someone who said this axiom is obviously true, and it's settled this important question, and let's add it to the list. And people would say, yeah, it's obviously true. Let's add it to the list. And in that case, then we would have had it now as one of our fundamental axioms, and people might have looked upon models where the power set size axiom was failing as very weird and non-set theoretic, in the same way that we now look, say, at models where AC fails or where the foundation axiom fails. They would be maybe curiosities or something. OK, so my argument is that the dream template cannot settle CH, because as soon as we know that a proposed principle implies CH or not CH, then we cannot accept it as obvious, and therefore the dream template is unworkable. So we have too much experience and familiarity with these universes of the contrary situation. And we understand deeply how those principles can fail. OK, there have been, of course, other attempts to settle CH, more sophisticated attempts. So Wooden has advanced arguments, first of all, using omega logic in the not CH case, and more recently based on his ideas on ultimate L. So he's not following the template. He's not following the dream solution template, but rather it's a more complicated argument. But a version of the objection still applies. Namely, to the extent that an argument aims to settle CH, what the multiversus desires is an account of the contrary worlds that we have such a rich experience with. So we want to know what was wrong, what was illusory about those worlds where we had the contrary situation. So we have an informed, deep understanding of how it could be that CH holds or fails, even in worlds close to any given world. It's difficult to regard those worlds as imaginary. OK, so I can talk about V equal L, but I really want to talk about the multiverse axioms, but I'm running out of time. So what I'm going to do is just I'm going to skip the V equal L material and go right to the multiverse axioms. OK. So I want to become a bit more speculative and provocative here by proposing multiverse principles, proposing principles that express the properties that we expect to be true in the multiverse. So I want to be provocative. So the principal multiverse idea, of course, is that there should be a huge collection of universes, each of which is a model of some kind of set theory. But we don't have to consider all the universes in the multiverse equally. We can simply be more interested in the parts of the multiverse consisting of universes satisfying some very strong theories. And there's no need to draw sharp boundaries. We can regard some of the universes as more set theoretic than others. So the multiverse really, the view is that the multiverse should be expansive. It should be as big as we can possibly imagine. At any time, we're living in one of the set theoretic universes using a particular set concept. But there are these other set concepts that we could use and move to. So we don't expect individual worlds to access the whole multiverse. And Penelope Matty used the maximized principle, the idea that there should be no undue limitations on set existence, to explain the set theoretic resistance to the axiom of constructibility. But similarly here, we can follow a second order version of maximize. We want to place no undue limitations on which universes exist. So I'm appealing to a second order maximized principle in terms of existence of universes. Okay, so the most basic axiom, of course, is that if you have a universe and you have some definable universe inside of it, then W should also be a universe. So this gives me things like the L and the hot and the L of R and so on. Of any model, if I can define something inside of it, then this is counting as a universe. Also, the forcing extension axiom, for any universe and for any forcing notion, there is a forcing extension by that forcing notion. There's no expectation that those are the only ones. Next comes what I call the mirage of tallness. Every model of set theory, of course, imagines itself as very tall, containing all of the ordinals. But of course, it only contains all of its own ordinals, and other models may not agree that those are very tall. So the top extension axiom says for every universe V, there's a much taller one that, into which the original one embeds to an initial segment. So we can extend any universe to a much taller universe. Every model of set theory imagines itself as enormous, certainly uncountable. But of course, we know that models can be mistaken about this. So there can be countable models of set theory which do not realize that there's a much larger model of set theory surrounding them. Of course, countability is a notion that depends on the set theoretic background. Whether a set is countable or not depends on the set theoretic context in which you ask this question. So on the multiverse perspective, the notion of an absolute standard of countability falls away. So we have the principle that every universe should be countable from the perspective of another better universe. Set theorists have traditionally emphasized the role of well-founded models, transitive models. But the concept of well-foundedness, of course, depends explicitly on the set theoretic background in which it's considered, right? So whether a particular relation is well-founded or not depends on the model of set theory in which this question is asked. So, so how can we talk about well-founded models as though this is an absolute concept when we know very well that it is not an absolute concept? So this issue arises even with the natural numbers, where we have the curious situation. So when you say the numbers 0, 1, 2, 3, and so on, the question is, have you described a unique mathematical structure or not? So many people appeal to, say, the categoricity proofs of Peano to say, yes, that's a unique structure because there's only one model of the natural numbers. But of course, we already know that different models of set theory can have different non-isomorphic natural number objects in them. And so the categoricity argument is an explicit appeal to a second order quantifier, namely the categoricity argument has to do with what subsets of the natural numbers exist. So if we have given up on the idea that there's an absolute set theoretic background, then it seems we have no basis to make that categoricity argument, and therefore no reason to think that we have coherently described a unique mathematical object when we say 0, 1, 2, 3, and so on. So the mirage of well-foundedness axiom makes this explicit. Many people don't like this one, so this is my most provocative principle, I think. Every universe is ill-founded from the perspective of another better universe. So there is no, the principle says there's no absolute background concept of well-foundedness. It's always relative to a universe, and all of the universes are wrong because there's a better one that looks upon that universe as ill-founded. Okay, so here's some more. So when we're living in a universe and we have an ultra-power embedding, say, then it's very common to iterate these maps forwards. You have a map J from V to M, then you look at J of J and J of J of J and so on. You make these forward iterations. It's an extremely common idea. The later models have their maps, and they don't realize that those maps have already been iterated many times. So the multiverse idea here is that, well, whenever you have an embedding, then in fact it has already been iterated. There's some other universe W and an embedding H, so that J is the iterative H. So in other words, the axiom says every embedding has already been iterated many times. Absorption into L. So this is, it's a fact that every countable transitive model of set theory can be continued to a model of V equal L. In fact, it can be continued to a pointwise definable model of V equal L. If you have any countable transitive model of set theory, then there's a larger model of set theory that thinks V equal L is true, which contains that original model as a transitive set. So the absorption into L axiom says every universe V is a countable transitive model inside another universe satisfying V equal L. For all we know, our current universe is a countable transitive model inside a model of V equal L. So, okay, it's fine to just propose a bunch of principles, but are they coherent? And my answer to that question is the following theorem, which I proved with Victoria Gitman, namely that, so it's a question of formalization. The multiverse axioms are not stated as formal axioms in any formal system because they're intended to be axioms about the full real universe, and we can't even state these axioms even in the higher order set theories that are available. So the toy model formalization is the version of those axioms that's talking about tiny set models, and there we are able to make a formal statement and interpret the axioms give them the toy model interpretation. So we can talk about a multiverse of sets. It's just a collection of models of set theory, and they can satisfy the axioms if that collection of models exhibits those closure properties that the axioms are expressing. So with that toy model formalization of the axioms, the theorem is that if CFC is consistent, then the collection of countable computably saturated models of CFC satisfies all of the multiverse axioms. So for example, every countable computably saturated model, so also known as recursively saturated, every countable computably saturated model of CFC is a countable transitive model inside another such model which satisfies V equal L, and also inside another model which looks at the first one as ill-founded. So they're all ill-founded, and they're all ill-founded from the perspective of another one of them. So I take this theorem as evidence that the multiverse vision expressed by those axioms is not incoherent, because here is a situation in which all of those axioms are true. So let me conclude by just saying that on the multiverse view, the task of set theory is not the search for the one final true set theory, but rather it's to explore all of the various interesting set theories that we know of and to find new ones and to discover how they are related. The philosophical debate will not be settled by a mathematical proof, but a philosophical view suggests mathematical questions and topics as interesting, and one measure of the value of the view is the value of the mathematics to which it is led. So I take the philosophical debate here to be a proxy for the question, where should set theory go, and which mathematical questions should it consider? So thank you very much.
Questions?
I'll keep it.
Oh, okay. Well, as long as I have to, I have to get going, since I just wanted to ask a few questions.
Sure.
Well, a few points.
Sure.
As I go through this. The first thing is, I think maybe it's just a slight point that I think a generic extension is more like a transcendental field extension, not an algebraic field extension. It's more like adding a transcendental element.
Sure, I agree. Yeah.
The other point is that the analogy with
But hang on, though, because sometimes when you add the generic filter, it's uniquely determined and definable in the extension. So both kinds of extensions are
well, I mean, transcendental elements are interrelated.
No, but some forcing extensions, the generic object is definable without parameters.
Well, I
So
in
this is, so it's algebraic. I mean, it is algebraic in the monotheory
well,
sense. Right?
the other thing is that the analogy with Euclidean geometry versus, I don't really have the sense that it's really that accurate, because on one hand you have highly constrained reasons why you have certain kinds of geometries, and you don't have, you have a kind of freedom with forcing models of set theory. It's such a lot more in some sense.
So it's different just because the possibilities are
yes,
more.
where there was an evolution, in historical evolution of mathematics, in which a semantic interpretation within Euclidean geometry allowed you. So there was this issue of having certain kinds of semantic interpretations,
right,
but they were quite constrained to a few kinds of geometries you could create within Euclidean geometry. So it seems a little bit a different kind of an approach you have.
Well, so is it really different, though? I mean, it just seems to be a difference of degree rather than of kind. I mean, are you just saying that there's fewer geometries?
It's constrained mathematically, whereas forcing seems to be unconstrained in ways. the axioms are so weak in set theory that you can practically do anything, so to speak.
I see.
Whereas in geometry, you have a lot of constraint about what kind of things you would like to have. Hyperbolic geometries of certain sorts and so forth.
I agree with
the
that.
main thing is, I don't know why it's necessary to have a gloss of realism, like in an early street.
Right.
What is the philosophy of set theory? Why do you need to be a realist, or why make any decision about that? Why tout that? Why not present an interesting mathematical point of view about a mathematical subject? Prove the Hamkins result is very interesting. Why must one say there's something about realism about that? Why must
Well, I mean, my point, my take on that is that, sure, you don't have to. You can have a multiverse view which is formalist, but my point is that you don't have to go to formalism to have a multiverse view. It's compatible with.
Why have any kind of? These are very, I think, belabored and vexed old philosophical stances, formalism versus Platonism
Right,
and all that.
but
why have all that? Why?
But that's an objection that applies equally to just the universe view as to the multiverse view.
Yes.
So that's not a multiverse-centered objection.
I'm not saying
Yeah.
it's, but I don't see why one has to have. Yeah, I have a similar objection to Wooden's realism. It doesn't
Right.
mean anything to me, but I just don't understand why it's necessary to have one view or other from these very, vexed questions about formalism, and which I don't think has much to do with mathematics and set theory as progress and methods and so forth.
So let me offer an answer, though, particularly in the case of the multiverse view rather than the universe view. Because if you just adopt a purely formalist position, then it's difficult to talk about the relations between the various models, between the various universes. If you're committed to a sort of real existence for these different universes, then the question about how they relate to each other seems to be more sensible than it is on a purely formalist account. I mean, of course, when they're definable and so on, then you can do it on a formalist account. But
let me ask you, the thing is, you seem to think there's something bad about formalism, but it's not even just, it's just a mathematically interesting venture to study different kinds of models. They're not necessarily formalist. And also, I don't agree that it's really something about the concept of set that's always being turned around. You're just trying to verify most situations, some axiom is something about large cardinals. The concept of set as such, which is some sort of underlying grounding for something, doesn't seem to be getting changed that much. You're just studying, Feiling's axioms interesting, this axiom, these things are interesting things, and how can we construct new interesting groups, new fields that do certain kinds of things, but they don't somehow change the concept of set drastically.
But when you're talking about a set-theoretic universe as a sort of world of mathematics that you could jump inside and live in, then it does seem that you're changing the underlying concept of set. You're changing the background concept of set so that when you ask your mathematical question using this concept of set, you get a different answer than when you ask it using this other concept of set, which is maybe a forcing extension of that one. So it seems that you do get some traction thinking about it as a concept of set, particularly when you're asking about how other mathematical truths can vary and depend on the background concept of set where the question is asked.
Well, okay, I would disagree with it.
I guess there's a question. Oh, go.
I have a comment about the
Sure.
paradox of the universe view
Right.
and the dream solution.
Sure.
So you and I have talked about this a lot. So the paradox of the universe view is the existence of model theory. So you can construct different models of different theories of different formal systems of set theory, and that's supposed to be a paradox for the universe view. But it looks to me like the universe view advocate and the advocate of the multiverse view end up talking past each other, because to the universe, the advocate of the universe view, those constructions all just produce sets which exist back in V. So the existence of model theory doesn't threaten the universe view. That on its own is not a paradox for the universe view any more than the existence of non-standard models of number theory is a paradox for a person who says, oh, I'm studying the natural numbers.
So, I mean, my reaction to that is that No, it's not really correct, because when you have the universe view and you're committed to a certain universe, I mean, apart from Aki's perspective, but if we have this realist view, then with respect to a certain set-theoretic background, these other sets that exist in these alternative universes simply do not exist in this concept of set. And it's incorrect to say that they do. You have to go to the larger set concept in order to have the L generic filter. If your concept of set is based on the axiom of constructibility, then you simply do not have your L generic Cohen reals. But in the larger set-theoretic context, which is not based on that original set concept, you do have such L generic Cohen reals. And so the concept of set has indeed changed when you go from one model to another.
The advocate of the universe view is going to pitch forcing by saying you start with a countable transient model, you build something inside V. And they're going to respond to every gesture you make toward constructing outer extensions of V by saying, well, wait a minute, is it a set? V consisted of the sets, the well-founded extensional objects. If it has those earmarks, then it's not outside of the original space.
Okay, but this is like saying that, okay, you're living inside the real numbers, and someone says that I have this other number I whose square is -1, and so you say there is no square of -1, no, it just doesn't
because
exist.
Because -I, the root of -I is not a real number. But these things, by your own admission, are sets. The idea of the set-theoretic concept is that it's expansive. It includes anything that's well-founded extensional. If you produce something with those earmarks, I'm just speaking from the advocate of the universe view. So
well, this is
it looks like the two people talk past each other.
Yes, it was happening. So the point is that the multiverse attack on that argument is that it's not correct to say that you have all the sets. When you say that I have there is no concept of set that really includes all the possible concepts of set, because for any concept of set, we can build from it another concept of set corresponding to the forcing extensions that gives me more sets than you had in that one. And so there is no concept of set that includes all the sets for that reason.
We just hit the dream solution
Sure.
first. So I also thought that went a bit quick. Consider the analog of the dream solution for new axioms that settle an undecided statement in arithmetic.
Right.
So let's say we're at the time where Goodstein's theorem is not a theorem, and it's shown that it's not provable in PA. Someone comes up with a dream solution. Find an axiom which will imply this or imply its negation. Someone does. Epsilon naught is well-founded, or there's a multitude of other axioms. You can work with second-order arithmetic.
Right. Sure.
And you get it. And then the community's response is, done. That's why Goodstein's theorem is called a theorem. Your response in that setting would be, wait a minute, we can construct models of arithmetic where it holds and models of arithmetic where it doesn't. So we're just like we were in the CH case. Therefore, that's not a dream solution.
No, it's not correct, because we had no examples of models that seemed fully number theoretic in saturating our concept of number where Goodstein's theorem was false. We had these weird non-standard models that were based on failures of consistency, and we knew that they were not really fully expressing the concept of number that we wanted. So they were not fully number theoretic. We didn't accept them as the real natural numbers. So the situation with CH is totally different, because we can build these models of CH and of not CH, well, the forcing extensions. We can build models of not CH that seem fully set theoretic to us in a way that the models, the non-standard models of the natural numbers did not seem fully number theoretic to us, because we knew that ConPA was failing in them and so on, but that's a principle that we're committed to. So it wasn't symmetric there. We didn't have models of the failure in the same way that we have models of the failure and of the positive version of CH. So I don't see them as anomalies.
Yeah, I have a little trouble seeing how you reconcile your response to Peter's question about Goodstein's theorem with the implicit view in your multiverse axioms that the notion of well-foundedness is completely relative. So in any one of these universes, there will be some, let's call it a higher universe in which,
Oh, I see.
which so to speak recognizes the non-well-foundedness of the lower models. So and therefore, I think it probably is going to involve in the larger language a failure of mathematical induction.
Oh, I don't quite understand that last part. So,
Well, in a non-standard model, there, at least looking at it from the outside, you always can describe it failure of mathematical induction.
oh, I see. So you're saying because sort of meta-theoretically the induction is failing because it's ill-founded model, then sort of ultimately induction is failing forever. So, well, let's see. So how should I respond to you? I mean, the answer to Peter's objection was that in the case of CH, we seem to have equally good, equally satisfactory set-theoretic seeming models where CH is holding and where CH is failing. But in the case of Goodstein, even within one set-theoretic universe, we have it holding in that universe's standard model and failing only in that universe's non-standard models. And so there's not a symmetric situation where they seem somehow equally valid.
It's just because I didn't choose an ORI sentence. CH is an ORI sentence, but I'll choose an ORI sentence.
Okay, but if you
Take a
choose an
delta
ORI
02
sentence, then it's much more problematic in terms of whether it really is true or
Take
not.
a delta 02 ORI sentence for PA that's implied by ZFC. You can easily construct it.
Okay, but then if it's implied by ZFC, it will be true in the standard model of any multiverse, of
Let
any
me just finish
universe.
it. With that, you can take a model of arithmetic and extend to turn it on, extend to turn it off. You can flip it on and off.
Yeah,
So
yeah,
it's
but
just like
within
CH
any
is.
set-theoretic universe, it's going to be true. So therefore, we're not having a substantive number-theoretic sense in which it's equally true and equally false. If you take an ORI sentence for ZFC, then your argument on that part is getting some traction, but then the other part fails completely because we don't really know whether we should take it as true or not, precisely for the reason that we can turn it on and off.
Well, you can just choose one that's implied by ZFC plus inaccessible.
Well, okay, so then, I mean, of course, one can play this game and keep pushing up the large cardinal hierarchy, but then the answer is, well, so there's this asymmetry happening, but to what extent are we really sure? You know, as you go high up enough, you might as well just be talking about the large cardinal in the first place instead of the ORI sentence.
Well, I thought you were radical pluralist, so I thought you were going pluralist on arithmetic too.
I am, yeah, but in the context of set theory, right? I want to have my arithmetic inside a model of set theory.
But for the same philosophical reasons, you would give another talk on the multiverse view of arithmetic, and then you would say all the things that you're saying about CH.
No, I wouldn't, because we're committed to the set theoretic concept, in particular the axiom of infinity, which is implying Goodstein's theorem is true, and therefore we're committed to the idea that Goodstein's theorem is really true. It's true in every single standard model of any model of set theory in the multiverse.
Okay, we have 1 minute left, so I guess it's okay, stop. Single speaker.
Thank you. Right, so the question is, if you're sort of a multiverse in set theory, does that mean that you're not committed to anything beyond PA? Oh, sure, yeah, great to see you. Glad you could make